Welcome back to Tracing the Sky. So in the last video, we finished off Aristarchus's journey, or at least as far as he got in his lifetime. He was able to relate the distance to the moon and the sun and their sizes back down to the diameter of the Earth. So if he's able to figure out what the diameter of the Earth is, he can figure out the size of the moon, the size of the sun, and their distances. Now, he wasn't able to figure out the diameter of the Earth in his lifetime, but somebody else was shortly after. And that's who we're going to focus on today. So let's just remind ourselves of those equations Aristarchus came up with, what he needs and how he can relate them, and then let's add the next piece of the puzzle. The good news is the method for figuring out the diameter of the Earth uses geometry we've already looked at, some really basic geometry, and a little bit of knowledge about how far away a place is. So let's have a look at Eratosthenes and how he figures that out. So this is just a quick refresher. Remember, Aristarchus was able to boil down the relationships to 4 simple equations. Each of these relates something he wants to find out, like the moon diameter, to the Earth diameter. So if he can figure out the Earth diameter, he can figure out each of the pieces of the puzzle he wants, right? The moon diameter is equivalent to the Earth diameter divided by 4, or the moon distance is just 30 Earth diameters. Sun diameter is 4.75 Earth diameters, and the sun distance is 570 Earth diameters away. So if somebody can figure out the Earth diameter, they can finish what Aristarchus started and solve the problems. So now let's look at how Eratosthenes is going to find the Earth diameter. So Aristarchus lived between 310 and 230 BC, and Eratosthenes was 276 to 194 BC. So you can see that they overlapped a little bit. They actually both knew Archimedes and would correspond with him, and from what I've gathered, Eratosthenes was familiar with Aristarchus's work, and it was actually really foundational for his work. Now he's going to figure out the diameter of the Earth in about 240 BC, so about 10 years before Aristarchus dies. There is some suggestion that Aristarchus actually heard about his discovery and knew about it, but I'm not 100% sure about that. One of the challenges with this sort of thing is a lot of their original works were lost, and we know about them from secondary sources. But anyways, let's focus on Eratosthenes and what he is able to figure out, because he's familiar with Aristarchus's work, and one of the things he's going to be interested in doing in his lifetime is figuring out the diameter of the Earth. So what I have set up here is just a foundation piece that we need to understand. So here we've got the sun on the right-hand side, and we've got the Earth. So sun over here, Earth. And what we've looked at with Aristarchus is how to think about shadows, right? We talked about how the light coming off the sun kind of converges here, and that the shadow will be placed here. And that's why the shadow gets smaller, because the sun's really big and far away, and the light kind of converges here. Now, one thing I mentioned that I just want to reinforce is that it's not like there's only light going in these ray directions. Light is coming off the sun in every single direction. And it's not really like straight lines. It's more like a wall of light, you can think of it, is emanating from the sun. Now, why that's important is you can think about the light that's between our shadows here, right? So all of the light here as coming off in straight lines. You can imagine light coming off of the sun and hitting the Earth in these parallel straight lines. Okay, so we've got light hitting the Earth in parallel lines. So no matter where you are on this side of the Earth, the light coming from the sun is coming at you in parallel lines. And you'll see why this is important. Okay, so why is this important? Well, in addition to knowing how the light is hitting the Earth from the sun, he knows the distance between Syene and Alexandria. He knows that they're about 500 miles apart. He also knows that on a particular day of the year, at noon, the sun is directly overhead. And how does he know that? Well, remember, we can measure the altitude of the sun based off of the length of the shadow. The higher in the sky the sun is, the shorter the shadow of the stick. Now, if the sun is directly overhead, right, 90 degrees at the zenith, there will be no shadow, right? The sun will be coming directly overhead the stick and it won't be casting a shadow in any direction. So he knows that that must mean that the stick or the gnomon is parallel to the light coming from the sun. The light is essentially coming at the stick directly overhead. It's coming at the stick directly overhead. So it's not casting any shadow. Now, what he does is from Alexandria on the same day that he hears that the sun is directly overhead, he measures what the length of the shadow is there. He measures the length of the shadow, right? So this light coming off of the sun is going to be parallel and it's going to be blocked, right? There's going to be lots of light coming parallel and some of that light is going to be blocked by a gnomon in Alexandria and it's going to cast a shadow. Let me just draw that shadow in red for us. So this is the shadow. Now it's going to be obviously much smaller, but this is the shadow being cast here. Now, why is that useful? Well, before I go on, I want you to pause here if you're interested and try and think about the geometric principles you know and whether you can solve this. You might not have enough information yet, but I want to give you an opportunity to try it out for yourself. So pause, think about it a little bit and see if you can figure out the answer and then come back and I'll give you another little hint and I'll keep giving you one hint at a time to see if you're able to apply everything we've learned so far to solve this problem. Okay, so the next step is to imagine extending your stick directly down. If you go up, remember, it's the zenith. It's directly overhead. It's exactly perpendicular to your horizon, right? And so if you were to drill all the way down, right, extend the stick all the way down, you would have something like this, right? It would split the earth in half and it would pass through the center of the earth, right? It would pass through the center. So here's our center. Now, if you do the same thing with the stick at Alexandria, it's also going to split the earth in half, right? You could split the earth in half from anywhere on earth as long as the stick is exactly perpendicular to your position, to your horizon, right? So they're going to meet at the center. And what you can see is that you're left with a slice of the earth, right? You can imagine doing something similar with a pie, right? If you cut a pie directly in half and then directly in half again, and you pass through the center, you're going to be left with a slice. Now, what you can see is that Eratosthenes knows the distance here, right? He knows this is 500 miles apart. And that is a portion of the circumference. You can think about it this way. You're making a slice of the earth with a portion here that is 500 miles apart, right? You can think about measuring that on a pie that you cut yourself, right? You could measure that outer portion and that would represent a portion of the circumference. Now, notice this. If you knew how many slices of this size you could fit in this circle, then you could figure out the circumference, right? If you knew that you could fit, let's say, 10 slices of this size in the earth, then you would know that the circumference of the earth is 5,000 miles apart. And we'll look at why that's significant in a bit. But what Eratosthenes knows now is, okay, I know how big this slice is. It's 500 miles apart. If I can just figure out how many of these slices there are in the earth, I can figure out that answer. I can figure out the circumference of the earth, and using the circumference, I can figure out the diameter. So pause here and think about how you might figure out the number of slices, and then I'll show you the next step. Well, how can we figure out the number of slices of this size that fit in the earth? We know that the size of this slice is 500 miles, at least from this perspective. So one way you could do it is walk around the entire earth to get the circumference and then divide it by 500 and you would get the number of slices. So if you walked around the entire earth's circumference and measured 5,000 miles, you could divide it by 500 and discover that there are 10 slices. But we want to do something more efficient, right? That would take a lot of work and probably be impossible. So how can we figure out the number of slices without knowing the circumference of the earth? Well, Here's one thing we know. We know that there are 360 degrees in a circle, right? And what else we know is that the size of this slice could be measured as 500 meters from this perspective or 500 miles from this perspective, but we could also think about it as an angle. We could think about it as the amount of turning we do from the perspective of the center of the earth, looking out at Syene and turning to Alexandria. So we can measure this slice as the amount of turning we do here. So if you knew what this angle was, you could divide 360 by this angle and find the number of slices. For example, if this angle was 10, if it was 10, you could divide 360 by 10, and you would know that there are 36 slices, right? There are 36 slices of this size in this circle, in the earth. Now it's not 10, so how can Eratosthenes figure out what this angle is? Because if you can figure out this angle, he can solve this problem. Now, I'll tell you, you already know the geometry to solve this, and I think you might have enough information on screen right now. So I really encourage you to pause before I give you the next hint. You might remember this geometric principle, that if you have two parallel lines, and there's another line going through them, that all four of these angles have to be the same as one another. That the only way for these angles not to be the same is if these lines were not parallel. Now we won't go over that proof again, we've done it in a previous video, so hopefully this sparks your memory. But remember, if you have two parallel lines and they're intersect with a line like this, the angles have to be the same. They cannot not be the same. So here's a question. Do you think you can figure out what this angle is, right? This angle here, the angular slice of this earth, pi here. Can you figure out what this angle is by measuring something in Alexandria? Can you measure something in Alexandria that will help you figure out that angle? And like I said before, if you're starting to see the next step, pause and try it out for yourself before you keep watching. So hopefully you've had a chance to think about this. Now, if I move this label out of the way, what if I extend this stick up in the other direction? Right now I have two parallel lines here, right? I have two parallel lines. Remember, the stick and the sunlight are exactly the same. So the light is parallel, therefore the stick and light together are parallel to just the sunlight here. Well, this looks an awful lot like this now. And I can measure this angle here. This angle here is going to be the same angular size as the slice, which is also the same as this angle. Now, maybe you can solve this. Pause again if you're seeing it and don't want me to give you the answer yet. But once you've had a chance, we can continue. So hopefully you've thought about it a little bit. Well, you might recall that this stick is perpendicular to our horizon. So it's a right angle. It's a right angle. And you might remember from when we were measuring the altitude of the sun that we can figure out the angles of our right angle triangle just by knowing the length of the sides. And we know the length of two sides here. If we know the length of two sides of a right angle triangle, we can figure out the angle. So if you measured the length of the shadow here, and the height of your stick, you would be able to determine the angle here. You would be able to determine this angle here. And using this angle, you would know this one, right? This angle here is the same as this one. How cool is that? By knowing a little bit about right angle triangles and some geometric angular theory, you can figure out that this angle here is the same as this angle, which is the same as an angle measured at the center of the earth of your amount of turning from Syene to Alexandria. How cool is that? So, this is exactly what Eratosthenes does, and he gets an answer. He figures out that the angle is 7.2 degrees. So he knows the size of the slice of this pie. It's 7.2 degrees. Now, before I go on, try pausing here and figuring out how many slices fit in the earth. If you have a slice of 7.2 degrees, how many slices of 7.2 degrees can you fit in the Earth, and then see if you can figure out what the circumference of the Earth is. So pause here and come back once you're ready. To find the number of slices, you just have to take 360 and divide it by 7.2. And if you do that, you will get 50 slices. Now we're rounding a little bit here with some of our numbers just to make things nice and clean. But the important part is the methodology is 100% correct. So what Eratosthenes knows is that there are 50 slices where the portion of their circumference is 500 meters, right? And the angle is 7.2 degrees. So you can make 50 of those slices. So now we can figure out the circumference of the Earth. The circumference of the Earth, is equal to 50 times 500 miles, right? 50 times 500 miles. And if you do that, you'll get that the circumference of the Earth is equal to 25,000 miles. So the circumference of the Earth is equal to 25,000 miles. 25,000 miles. So Eratosthenes knows the circumference of the Earth is 25,000 miles. Now, we don't need the circumference, remember, we need the diameter. So maybe pause here again and see if you remember how we can relate circumference to radius or diameter. We've already done this with Aristarchus. There is a relationship and it has something to do with pi. So maybe you can remember that relationship. So let's round this journey off by plugging in our numbers. Remember, the moon diameter is the Earth diameter divided by 4. So you take our Earth diameter of 7,957 miles, you divide it by 4, and you will get 1,989 miles. That's only a couple hundred miles off from the real answer, which is 2,159 miles. That's the diameter of the moon. Look how close that is. It's amazing how close they got, given how long ago they were doing this. The distance to the moon is 30 Earth diameters. So here you multiply those out and you'll get 238,710 miles. The real answer, again, only off by a couple hundred miles, is 238,855 miles. That's the actual distance to the moon. Again, they're only a couple hundred miles off. Now with the sun, it gets a little bit more erroneous because remember, Aristarchus, because he measures at the wrong angle, thinks that the sun is only 19 times larger and 19 times further away. In fact, it's about 390 times. So if you multiply the moon diameter by 19 and the moon distance by 19, you're going to get that the diameter is about 41,000 miles for the sun and the distance is 4.5 billion miles. Well, that's way off because you have to multiply it by 390. You get a lot closer when you do that, right? 775,000 miles to the 865,000 and 93 million miles is about the right answer. So you get pretty close when you use the correct 390 ratio. But when you use 19, you're way off. Well, thank you again for taking this journey. I hope you can see why Aristarchus is one of my favorite astronomers. Right? Using some simple principles of geometry, some incredible imagination and creativity, he's able to solve this crazy audacious problem he started with, trying to figure out the distance to the moon and the sun and their sizes. Now, yes, he makes some mistakes in his measurements, but the reasoning is bang on and sound. And so I hope this shows you the power of the human mind and what you can do with geometric principles and some knowledge about the world. And Eratosthenes is able to pick up right where he leaves off, right? He's able to figure out the diameter of the Earth using very similar principles. So we're going to continue our journey next time, looking at other astronomers and what they're able to do. But I hope you enjoyed this mini series on Aristarchus. I'll see you next time.